Hi, everyone. I'm Bárbara Rojas Ayala. I'm an associate professor at the Instituto de Alta Investigación of the University of Tarapacá in Chile. And I was invited by the organizers to give a talk about the host stars. I was very, I think, ambitious with this because I gave it this very uh, big title, right? 25 years of exoplanet discoveries. What have we learned so far? We have learned a lot, and I don't think I can cover everything in 1 hour. So I'm gonna just try to cover what I think it is important when we're talking about exoplanets and about the stars that are hosting them. So, um, so why do we care about the stars? And we should care about them because the detection methods that we have right now, the most successful ones, are indirect methods. And therefore, the exoplanet properties depend on the observables and the fundamental parameters of the stars. Here I have two examples, for example, of observables that we get from radial velocity and from transits. And we can see there that they do depend on the mass of the planet and the radius of the planet, but they also depend on the mass and the radius or size of the star. Okay. So, um, why do we want to know, for example, the bulk properties of the stars? Um, Probably you have seen this already. It's because we don't really just want to find the planets and say, look, that's an exoplanetary system. We really want to characterize those planets, and we really want to know if they are similar to anything that we have in the solar system. What are their compositions? And here I show you some plots related to radius versus mass for the planets. And you can see that the error bars can be quite large. And that doesn't help us to really constrain the composition for these planets. And those error bars depend on, for example, the error of the observables, but also on the precision that we have of the bulk properties of the stars. So why do we want to know the properties of the stars too? We want to know that because we want to know how planet formation works and how the evolution of those systems happen. We also want to know the properties of the stars for target selection of exoplanet searches. And this has been truth, I think, since the beginning. From the radial velocity surveys, um, uh, astronomers were trying to select the stars that were probably the best ones to find planets according to their technique. And even now, it's even more true when we think about the, the space telescopes, as Kepler, for example, that it had its own catalog. Um, TESS, Plato, Cheops. We also want to know the properties of the stars because we want to make sure that what we're seeing that appears to be a planet, it's really a planet. So we want to get rid of all the false positives that can happen, and they can be either related to the star itself, because it may be a binary, or it has a brown dwarf companion, or nearby it could have, binaries, or the configuration could be, um, for example, a grazing stellar binary. And also we want to figure out their rotations. Activity, for example, has been some of, I think, the topics in stellar astrophysics that has been more studied now that we found we're finding exoplanets. Um, some of the studies are related to, if those planets could be habitable. but also because activity can mimic, like the presence of a planet there. So how do we get precise bulk parameters or properties for planet hosts? And for that, we have to think like, what are the methods that we have that give us the most precise ones? From binaries, when we have a binary system, we can get the mass of the star and the radius of the star. And that's true, for example, for eclipsing binaries. And those probably are the best way to get masses, this fundamental quantity of the stars. The most precise way to get them. Getting masses of stars is actually really hard. It's not as easy if they're not in a binary system. Another way that, for example, we can get the size of a star is through interferometry if we know the distances. This was something that it wasn't that easy before, especially for the low mass stars before Gaia, because the previous survey, Viparcos, wasn't really sensible to these very low luminosity stars. And it was really, we didn't know the distances very well. Now with Gaia, that thing is going to change, and we can get, the radius of the stars without any problem. And there is another technique, asteroseismology, that it's very powerful, and it can give us, all this um, insight about the interior of the stars, like the mass. We can get the mass, the size, we can even get the age. We need to have an idea about the effective temperature of the star and roughly its metallicity. And unfortunately, it doesn't work for all the stars, because the stars have to have some shakes, right? It doesn't matter what causes them, but you have to be able to measure those ones. And right now, for example, there has been only theoretical work for M dwarfs. We haven't been able to find those signals for asteroseismology for the very low mass stars. So then we can think, well, that those are the ways that we can get really precise. But what about reliable? And that's fine. And I think that's what, the community has been done. Um, the What usually it's been done is that you try to get the atmospheric stellar parameters from high resolution spectra, for example, or another way to get uh, effective temperature is through interferometry um, with the parallax, because then you get the radius, and spectral energy distribution. Um, and using those atmospheric stellar parameters to get the bulk parameters for the stars. One example, it could be from spectra, from models. You can get the effective temperature of the object if you have the spectral energy distribution. So then you have photometry for this star, and you have the parallax using the luminosity equation. You can get an estimate of the size of the star. You can also get log G, for example, from spectra or from models. And with that and the equation of gravity, you can get the mass of the star. So those are ways that you can get those values. And it will depend on how well you can get those effective temperatures and how well you can get those surface gravities. And probably what it's being used the most, especially for the radial velocity hosts, is that you can use high resolution spectra. Usually, you can get the atmospheric parameters out of that spectra, and then using those values, you use stellar revolution models, and you get the mass of the star and the radius of the star from those models. So this will depend on how much you trust your stellar evolution models. Right now, there are different flavors. Some of them agree very well for example, solid type stars. For the cooler stars, they're the ones that I study, the results may not be so compatible. So then you have to decide which ones you want to use. Other things that I'm not really going to cover in this talk, it's other properties of the star that maybe we do want to know, especially when we're talking about trying to figure it out if what we're seeing there is really a planet or something else. And for example, that one of those things is rotation. You can get measurements of rotation by stellar spots, also by following, the light curves of of stars. We can figure it out if, stars like the sun, they're similar to the sun, are variable or not. And here, for example, there is an example between the sun and a star similar to the sun that it's way much more variable in brightness, right? And another thing that we want to know is activity. We want to know if there are flares, and we kind of measure activity using different indicators. Um, so activity is very broad, depending on what you think. And usually we try to characterize the stars either measuring H alpha or the calcium 2, H and K. Um, and we assign, a limit where we say, well, this object is active or not. Well, by seeing spots also we can give an idea of how active those stars are. So we're going to move on and we're going to talk about the characteristics of the stellar hosts. For that, I downloaded the huge table from the NASA Exoplanet archive. Uh, in January 4th of this year, there were about 4,324 planets in 3,216 systems. Okay, so this immediately tells us that there are stars that host more than one planet, right? We have systems with multiple planets. And what I show here is an HR diagram. So we have the luminosity and the effective temperature for these stars. And I tell you roughly the amount of stars that are plotted here. And it's less than the systems according to the table. And that's what, and you may be wondering, well, why is that? And it's because actually not all the hosts are characterized. We don't know the properties for some of the hosts. In this case, for example, we may not know the effective temperature and the luminosity, or the luminosity. We're missing masses, log G's, other quantities as well. The red dots that I'm showing in this plot are what I call like peculiar stars. It's usually not the objects that we can get the statistics out of their discoveries. Some of them are white dwarfs. We have also brown dwarfs that have planetary mass or size companions. B subdwarfs. We have also OB subdwarfs with red giants, etc. So now what I'm going to do is going to do a zoom really to, I'm going to take out those peculiar stars and I'm going to just work with what you recognize right there, right? It's the main sequence and the giant branch. So what I said before, about 70% of the hosts do not have effective temperature and or luminosity estimation by January the 4th, 2021. And that could depend because it can depend on the method of detection, right? As we're going to see in a little bit. So for example, here in purple, I'm showing you the radial velocity hosts, right? The radial velocity technique works better with bright, slow rotating, and inactive stars. Because for radial velocities, where we are measuring, the movement of the lines in this high resolution spectra because of the wobble, right? This kind of dance that the star is doing with the planets. Activity can be very tricky to get out, and even they can mimic planets. For this technique, it's way much more easy to find planets around J and K dwarfs, main sequence stars, and evolved stars. And this is basically what we're seeing in the HR diagram, right? We see radial velocity hosts in the whole main sequence and also in evolved stars. It's harder to find planets around F and earlier stars and in young stars. For the earlier stars, it's basically because there are not enough lines in order to do this kind of cross correlation and get these velocity shifts in the lines. It gets trickier. And for young stars, some of them are kind of broad, and that also affects, the calculation of these things. There are about 512 stars that are radial velocity host plot in this HR diagram. Now with radial velocities in the near infrared, there are way much more results for the M dwarfs because M dwarfs are broader in the near infrared and with young stars that can be probably embedded in something and they're not bright enough to get high signal to noise spectra in the optical. When we look at the transit host, we already see a difference, right? I'm gonna try to blink between these two. For the transits, they work best in bright, the technique works best in bright, small, and inactive stars. So that's very similar to what we have for the radial velocity hosts. Small objects because of the ratio between the sizes between the host and the planet. If the planet has it's large in comparison with the size of the star, then it's easier to detect it. It's easier to find planets with this technique around J and K stars, the same thing as radial velocities, bright M dwarfs. And here it's what we call the M dwarf opportunity. It's way much more easy to see, for example, an Earth-sized planet around a small star than a star like the sun. It's harder to find planets around evolved stars. And this is also because of this ratio between the radii, because they're too large. And it's harder also in young stars because of the variability. We're measuring, right, the brightness of the star, and the variability can be an issue. Most of the results that you see here are from Kepler, the Kepler mission, and now with some planets from TESS and Cheops, and soon Plato it's going to be up, and probably it's going to have more results. Here you can see it's mostly objects in the main sequence. There are a few objects that have evolved a little bit, but it's mostly objects in the main sequence. Another technique that has found planets, it's direct imaging. This is the only technique that it's direct. We're really seeing the planets. And for that, we have to go to nearby and young stars, right? Because if we're trying to identify the planet, these things are very faint. So either they had to be very, very close and also young. We need them to be young because that way they're still probably contracting and therefore they're more bright than when they are older. For direct imaging, it's easier to find planets around young A stars and around young and nearby associations. And basically this is what you see in this HR diagram, where you have all objects, when you go for temperatures of 5,000 and below, all of these objects are above the main sequence, and these are young stars. And then you have the stars towards the hotter objects. As I said before, it's hard to find planets around evolved stars and main sequence, just because of the contrast, right? We need those planets to be bright. And another technique that has found planets, it's the microlensing. Here you can see that I changed the plot, right? In the other three techniques, I was able to show an HR diagram. And I cannot do the same with the microlensing hosts just because we don't see most of the time, if not all of the time, we just don't see the hosts because in this configuration, the host is the lens. And what we see is the source, right? This is a star that is far away and that gets magnified by this lens that it's usually a star that we cannot see. And if we're lucky, that star will have planets and we can see the magnification of the star because of that system. Um, the microlensing best performance is in stars in front of dense stellar regions. In our galaxy, that will be when we look towards the bulge, right, towards the center of the galaxy. Easier to find planets around early M dwarfs, and that's because the majority of the stars in the galaxy are M dwarfs. About 70% of the stars in the galaxy are M dwarfs. So it's way much more probable that the lens, this object that we cannot see, it's an M dwarf, the one that's magnifying this star source. It's harder to find planets around nearby stars just because it's not very populated. And in, and and we need to, we need the configuration, we need the 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 source, to be affected by this lens and this light, um, basically send that to us, right, to create this magnification. As I said before, it's very difficult to characterize these stars. We usually don't have luminosities because we cannot see them, we cannot measure, we don't have a photometry. Um, what we can get out from the microlensing fitting, it's the stellar mass. And we also have an idea of the distance. From a stellar mass, you can get an idea of what is the temperature of that star, but that without the luminosity, we cannot really plot it in an HR diagram. And that's why I plotted this distance versus stellar mass and show you where these microlensing hosts are comparing with the rest of the stars, with the rest of the planet hosts. And you can see that they're really far away from us. Um, and usually are detected around objects that around stars that have less than one solar mass. So in the sky, how this, all of these hosts, where are they? So here we have a 2D representation of the sky. Everything has been color coded the same way as in the previous figures. So everything that is purple are radial velocity hosts. They could also be transit hosts, but I'm here using the technique that detected first the planet. In pink, we have the transits. Here you can see some places where there are way much more objects. It's very clear, for example, where the Kepler field is. And also you can see some clumps around, for example, in 6 hours and minus 60, or at 12 hours and 60, for example, at 18 hours and 60, for example. And those ones are the fields around the ecliptic that K2 has been trying to find planets around, also using the Kepler telescope. In yellow, you see the imaging planets, probably located to where the young associations nearby are. And we can see that the microlensing, the green ones, are very right there between at the 0 hours and zero, right there towards the center of the galaxy. If we do this in 3D, this is what we get, right? So we use the distances and that are given in the table of the NASA exoplanet archive, and use all of the parameters that I think most of them are from Gaia, the data release 2. You can calculate X, Y, and Z, and you can make this, 3D plots. So in black, we have the sun, so that's us. And we see that about in a radius of 5 parsecs, what we have are the radial velocity. We only have radial velocity hosts, okay? If we go farther away, for example, we go and see at 20 parsecs, we see that it's still the radial velocity systems dominate in number, but some of the transit and imaging systems start to show up, right? For the imaging is something that we expect because we know that those hosts have to be nearby and young and bright, so they have to be there. If we go farther away, 100 parsecs, we can see a way much more transiting systems, and we can see that basically the radial velocity system is kind of starting to be encapsulated by the transit systems. As we go further away, we go to 500 parsecs. That's very clear, right? We see that all the radial velocity hosts are located in the center, towards basically around our sun. And we see the Kepler survey contribution, right? This cone that it's coming out there, very populated with objects. That's the Kepler field in 3D, this cone coming out. At 1 kiloparsec, we start seeing some of the microlensing systems. And if we go farther away from us at 5 kiloparsecs, we see where really all of these microlensing planets are, right? They're very restricted towards the galactic center. And, at 10 kiloparsec, basically that's all of, that's basically where all of the hosts are. There is a white dot there that represents the galactic center. And you can see there that there are even a transit system or with eclipse variations or something that may be a planet. So now we're going to go and talk about the links between the properties of the host stars and the planets that orbit them. One of the things that has been very important um, for trying to get an idea which stars have planets, etc. It's trying to calculate these occurrence rates per type of star. And for example, results from RV surveys. Here I'm showing, for example, the occurrence rates per star from the HARPS and the Coralie sample. The first two plots are from Mayor et al. 2011, and they are for FJK stars. So about 50% of the solar type stars have at least one super Earth or Neptune, okay? For planets with periods less than 50 days and minimum masses between 3 and 30 Earth masses, the occurrence rate is 27%. You can, and here I show you that it's 15% from Howard Dow 2011, because here it depends on your survey. So you will find different numbers because usually these occurrence rates are calculated either for the Kepler sample, for the HARPS survey, for the Coralie survey, for the California Planet Search survey. They are specific for each survey. And they are there considering several things. What you see here, for example, in color, these lines in these plots of minimum mass and period are the detection probability curves according to their instrument, the capabilities of their instrument, and where have been they looking and how complete is the sample, etc. So so you can calculate them considering the mass and the period, for example, for the stars. The third plot that I have here, it's one that it's for M dwarfs. And the frequency of habitable planets, that's it's small planets. So the minimum mass is between 1 and 10 Earth masses. Around these stars is almost 50%, it's 0.41. So we can think that probably 40% of the M dwarfs may have an habitable planet. And that was huge when these results came out. It was really, really um, interesting because in the news and everything, it appeared that M dwarfs were, the best targets ever, and that's great for me because I study them. And we should study them because they're the 70% of the stars of the galaxy. But now that they have these, planets, they can have habitable planets around them. It's even cooler. Um, there's also occurrence rates from transit surveys. So as I told you, these ones are calculated specifically um, for each survey, just because each survey has their own characteristics in order to calculate this. Um, One of the earliest results that came out from the Kepler survey uh, was basically the brightest half of the Kepler main sequence sample um, from Howard et al. 2012. So here we have a plot where we have the number of planets per star with periods less than 50 days and ordered by stellar effective temperature. So Howard et al., they assigned roughly, um, according to those temperatures and spectral type to these stars. And what we can see here, and there are 4 lines here that represents um, the sizes of the companions, right? The planets that have been found. So in blue, we have large planets between 8 and 32 Earth radii. In green, it's between 4 and 8 Earth radii. And then we have the really small planets in yellow between 2 and 4 Earth radii, and then we have the total. In black, it's all the planets. And this was something unexpected. Kepler was a mission that was basically for FJK stars in terms of finding planets. And they realized that the most cool results that they were getting were around M dwarfs, right? So by measuring this, they realized that early M dwarfs were 7 times more likely to have a planet with periods less than 50 days. That is roughly 0.25 AU if we consider them to be circular, than the hottest stars in the sample. So that will be the F stars, the early Fs. Um, so that was huge. And I think, I'm not sure if these are the last results, but some of the latest results from Kepler um, for the habitable zone occurrence rates for FJK stars. It's with periods between 237 to 500 days, because it will depend on the spectral type of the star, right? Where that zone where liquid water can exist. It's about from 0.03 to zero point 0.4 for radius between 0.75 to 1.5 Earth radii. Okay, so that's for FJK stars. For the M dwarfs, that one is larger. So it's consistent basically with the results from radial velocity. For M dwarfs, the periods, of course, are smaller because M dwarfs are fainter and therefore they're cooler. So the zone where liquid water can exist is closer to the star. So the periods go from 0.5 to 256 days. It's about 33% for objects of the same size. Okay. There are plenty of papers and works about occurrence rates. Um, and these are just few of them. I just wanted to show you, for rate of velocity and transits that have been the most successful um, techniques to find exoplanets around stars. But there are plenty. And for example, you can go to this list that it's on the exoplanetary archive. They don't have all the papers with occurrence rates, but they have a lot of them. And if you're interested in this, go there, read them all. You can see that they are separated by kind of how it has been done. Now the Bayesian computation is really big, so there are a lot of that stuff. And our occurrence rates for specific planets with specific surveys. So if you're interested in this, you can go and take a look there. Another quantity that has a link, between this relation between the star-planet relation is its metallicity, either the iron abundance over hydrogen or the total metals over hydrogen. And one of the early results from the radial velocity surveys, especially because radial velocity was the first technique, basically finding planets around FGK stars. It's what is known as the metallicity giant planet correlation. In the early, after 1995, more planets were being discovered, and Gonzalez, I think, was the first one to look at this and realize that the fourth exoplanet host found till the day, I think it's a 98 paper, were metal rich. And the planets found around these stars were giants. And he proposed that pollution was the reason for this. Since they were fine planets, this material was going inside the star, and this material forming planets was inside the star, and that's why they were metal rich. However, the years passed. Actually, it's Gonzalez 97, and more results came out. And Santos, for example, was I think the first one that started talking about this giant planet and linking it to metallicity. And finally, Fisher and Valenti 2005 did a huge analysis with several stars using high resolution, high signal to noise spectra for FGK stars, and give this function of for the metallicity giant planet correlation. So what happens is that giant planet host stars have higher average metallicity when compared to field stars. Okay, so in this case, you have to compare the hosts with another sample of stars that they don't have planets. That's tricky, right? Because we will never be sure if that star doesn't have planets. We can say that that star doesn't have transiting planets, doesn't have radial velocity planets, but unless we actually search with every single method that we have, it's really tricky. So in this case, this sample of stars were stars that were searched also in radial velocity systems methods, surveys, and they couldn't find a planet up to a certain period or distance. The giant planet metallicity correlation provides a strong evidence of the core accretion being the main process of formation of giant planets. And this is something that probably you saw in the previous lectures that you had with planet formation. So this correlation favors the core accretion model. Okay, so here I show you two planet formation scenarios. There is recently a third one, a scenario that it's related to tidal downsizing, that it's not here, but hopefully you saw it. It's not in this figure. Probably you saw it as well in the planet formation lectures. So what about the accretion or the core accretion model? So in higher metallicity disks, rock and icy cores are able to form early enough to allow for runaway accretion. Okay, so what we want to do is basically grab a bunch of this material, rocky and icy material, to come really fast together before the star ignites and removes all the gas. So if this is done really, really, really fast, those cores can gather, start to accrete gas envelopes before this disk disappears, this gas disk disappears, and we can have these giant planets. When you have low metallicity, there is not enough material, so these cores cannot grow fast enough, and then the star ignites, and they haven't been able to accrete enough gas to become giants. Okay, and this is something that you can review in the papers that I show you there. There is the other formation scenario is the disk instability, and in that case, it doesn't depend on metallicity. So since the accretion model does depend on metallicity in terms of the amount of metals available to to form planets in the protoplanetary disk, this is why the giant planet metallicity correlation favors the core accretion model. Um, so basically that came out from the FGK stars. So what about other types of stars? For M dwarfs that host giants, in average, their metallicity is higher when compared to with field stars. And this becomes tricky because giants are not very common around M dwarfs. And we're going to see that in a couple of slides that follow. Here I show you some occurrence rates from the Neves et al. Paper 2013. Um, so these results came out from high-res, high signal-to-noise spectra of M dwarfs from the HARP sample, including also some of the stars from the California Planet Survey that were M dwarfs in order to calculate this. So for giants, we see that actually the M dwarf planet hosts are metal rich. But if we go and look at the low mass stars, it doesn't seem like it. And actually the relative frequency, it shows that they seem to be more metal poor. This is a tricky measurement. M dwarfs have complex atmospheres, and trying to get metallicities for them has been a huge problem, and still they're not as precise as the ones that we can get for FJK stars. So this result is solid. It's just that the errors are way bigger than what you will find for FJK stars. What about other types of stars? Giant stars, for example, because we were talking about FJK dwarfs and M dwarfs. What about giants? Well, the same thing happens. Giants that are hosting, Jupiter-sized planets have a higher average metallicity when compared with giants without planets. Again, we have to compare between samples that had been searched too. For example, here I'm showing the occurrence rate by Jones et al. 2016 that was calculated using high-res, high signal-to-noise spectra of giant stars from the Express radio velocity survey that have masses between 0.9 to 3.5 solar masses. Okay, so we see the same behavior as we go towards higher metallicity. There are more giant stars with giants. What about transits? All the previous results were from radial velocity. So what about transits? It's harder for transits because the detection is with photometry. And usually we want to calculate metallicity. What we need is a spectra. So we have way much more targets from transits, and trying to get a spectra out of them that is high signal to noise and high resolution can be very costly. So for some, it has been done, for example, from the paper that I'm showing here and the figure here. So there was a spectroscopic characterization of the Kepler host stars show that the planets larger than 4 Earth radii are found around stars with supersolar metallicity. Actually, it's defined that basically there are 3 regimes, and it's separated, by the radii. So we have the terrestrial, the gas dwarfs. I hate that name because it's very confusing, because it can get confused with dwarfs like the stars. And then we have the ice and gas giants. And here, we see these 3 steps. There is another paper that is from Schlaufman 2015 that it basically has the same plot and says that it's better fitted by a continuous line instead of this, a step-by-step metallicity. So what about small planets? It seems that smaller planets don't prefer metal-rich stars. And that has been shown in several papers. Here, for example, we have histograms where we compare giant versus Neptune planets for FJK stars from Gessi et al. 2010. In this case, they didn't have M dwarfs. And you can see that the Neptune hosts basically cover the whole space, and the Jupiter hosts not. The same thing, this is from one of my papers with really low number of planet hosts at the time in the radial velocity surveys. And we could see that actually the Neptune hosts were, were exhibiting metallicities that were not necessarily as rich as the giants. Um, so there doesn't seem to be a metallicity small planet correlation. You know, it's not something that it's there as evident as for the giants. And this is important, right? Because it tells us something about how the formation of planet occurs. Results from transits related to the small planet metallicity correlation. Here's a result from Mulders et al. 2016, where he found no difference in the occurrence rate of subneptunes as function of metallicity. However, if they're really close by, you see a difference. Small planets that are really close by, so with periods that less than 10 days, they do prefer supersolar metallicity stars. Okay, so that can also give you a hint about how planet formation works. There are other papers that have pointed out transient host star metallicity with planet orbital period distribution. You can check them there. I'm sure that there are more. For M dwarfs, it's harder to get these values. The metallicity values came out from the Lamost spectra of Kepler targets. This is not high resolution. So there also there is this probably has higher errors, and they're not as reliable as it for the FJK stars. Other results from the RV surveys is trying to find a metallicity planet distance relation. And this is from Adibekian et al. 2013, where he found that if he divided the hosts um, and highlighted them according to the most massive object that they have, if that is between 10 Earth masses and 4 Jupiter masses um, that are orbiting metal poor stars, are constrained to longer periods than those orbiting metal rich stars. So this is another thing, right? Like the distance. Um, and here, for example, you see those stars. I mean, you see those planets, sorry, not those stars. You see those planets um, that are orbiting in red, the metal poor stars, versus the crosses in blue, there are the metal rich stars. And you see that effectively they seem to appear in a different region, right? They exhibit larger periods for a given planetary mass. This can be, you know, look, this can be associated to planet formation. And basically, one explanation is that assuming that planets in a metal poor disk form farther out from their central stars, or do not migrate as far as planets in metal rich systems because they form later. This also has been found in higher mass stars, sorry, in higher planetary masses. And what about results from imaging, for example, the metallicity supergiant planet anti-correlation? Uh, and this is a result from directly imaging planets with masses less than 5 Jupiter masses tend to have metal-rich hosts. However, if we go to masses that are larger than 5 Jupiter masses, the average metallicity of the host stars show a declining trend. So we see that these stars exhibit a larger range of metallicities. We see this in other papers. In main sequence host stars in general, they show a trend of decreasing metallicity with increasing orbital distance for the planet. For example, something that was shown in the previous slides. And therefore, this is something that we can start thinking, well, maybe there's just not one way to form giant planets, and there are way much more ways, and they are all work together. For example, at larger distances, gravitational instability can play a role. There's also people that say that doesn't have to do with different things, that different methods to create planets, but it's really about what the material is available there. And that takes us basically to stellar mass. There are also relationships between stellar mass and the presence of planets. The stellar mass giant planet correlation also holds. And this is not surprise if you think that first I was saying, well, if you have more metals, you have more material. Well, if you have a larger disk, you also have more material to form planets. And ALMA results have shown us that something that we had assumed before, that the disk of the protoplanetary disk of the star scale with the mass of the star, is something that really happens. So if the star is larger, it's going to have a larger disk and therefore more material. And this is something, that could explain why giant planets are found less frequently around M dwarfs. We find giants around M dwarfs, but they're very little. They're a little number. It's not as frequent as we see those, for example, for FGK stars. And also this favors the core accretion scenario. However, some recent results have shown that the planet occurrence rate around giant stars, in this case, increases with stellar mass up to 2 solar masses. So we have this correlation, but then decreases at larger stellar masses. So for masses above 2 solar masses in giant stars, we have an anti-correlation. This could be because there is a slower growth rate, there is an increased migration time scale, and because these stars are larger, their lifetime of the lifetime of the protostellar disk is short, right? Because these stars will ignite faster than a star that is less massive. So you wouldn't find giant planets very close to the star now. That is something that, for example, it's easier to find with radial velocity planets. So here you have the giant planet correlation, but at certain mass, it becomes an anti-correlation. What about Neptunes? What it's been found, for example, from transits, and this is also from the Kepler mission, and it's because Kepler has been so successful finding Neptunes and sub-Neptunes and super-Earths, etc., is that sub-Neptunes occur more frequently around low-mass M dwarfs. Okay, so we see them. M dwarfs may not have giants, but they have plenty of Neptunes and super-Earths, and that's why probably in the newspapers in your country, you will often see a new Earth-like planet found, and usually it's around an M dwarf. This is not only a result from Kepler, also the same thing happens with radial velocity systems. However, the Neptune exoplanet population is most constrained by Kepler because of the detection efficiency that it has, that it's harder to get those planets from the radial velocities. And here is, a plot where you can see how the planet occurrence, within 50 days, I think it is. You have the planets per star versus stellar effective temperature, and you have spectral types here. And you see different lines here, and they come from different works. And you can see that the planets per star will change depending on the paper. And that's because their input in order to calculate these planet occurrence rates are different, even when they may be analyzing the same data. However, something that I want to show here is that independent of that, M dwarfs they do have way much more Neptune-sized planets uh, than FJK stars, no matter how you measure this, okay? This increase in exoplanet occurrence with decreasing effective temperature was discovered by Howard et al. 2012 with the with the plot that I showed before. The difference between these ones, as I said, is the detection biases and selection effects that each of these papers can use to calculate the occurrence rates, considering, for example, masses. Other characteristics of planet hosts. I wanted to show some of the results from asteroseismology. These are results that come out from Kepler, where you can get these measurements. And one of the results is that Kepler multiple planet systems have circular orbits. And this could be done only if you know the stellar density. So to know the stellar density, you need to have the mass and the radius of the star. And that's something that asteroseismology can give you with high precision. And therefore, you can have a really high precision for this density. This equation that you have here, the ratio between the density of the star and the density of transit that can be measured from the light curve, can give you an idea of the eccentricity of your planet, okay? So here we have, for example, the values that were obtained for a sample of multiple systems where the density of the star was calculated from asteroseismology, and then the density of the transit was calculated from the light curves. And we see that most of these planets, these systems with multiple systems, their planets have orbits, but have a density ranges that are closer to 1. That means that basically the eccentricity must be 0 or close to 0. So they have circular orbits. Something that we know, result from Latham et al., I think 2011, is that Kepler multi-planet systems preferentially contain small planets, and therefore small planets tend to have circular orbits. And you see here also the distribution from the radial velocity planets, and you can see that they tend to show a different distribution, basically. They show that some of the values that they have are not necessarily concentrated in one, and therefore the radial velocity planets exhibit eccentricities. So this is a very specific result for the Kepler sample, right? So that's why the Kepler multi-planet systems tend to have circular orbits. This is important because eccentricity can impact the habitability of exoplanets. You know, depending on where it is, if it's a very eccentric orbit, it could be that in part of the orbit the water can be liquid, while in other parts of the orbit it's not. And also here you have the plot of what happens between pre-Kepler or K2 and what happened after Kepler, and how many of these stars were had values measured from asteroseismology. Another result from asteroseismology it's related to having a 3D view of the star-planet system. So in this case, this has to do with angles and what we're seeing. So asteroseismology used with transits and RV basically can give us this 3D view of the star planet system, and we can learn how the star is located with respect to the orbit of the planet that we're seeing. In these angles that we have here, basically we have the obliquity right here, that it's composed by the inclination of the star with respect to the line of sight, and this inclination angle it's measured with respect to the rotation vector. And here you have the inclination of the planet that it's related to the normal, to the disk. And in this case, using, for example, the inclination of the planet from the transit light curve, lambda that you have here, that it's basically the projection in the 2D of the obliquity, from RV data from the Rosity-McLaughlin effect, and the inclination of the star from asteroseismology, they were able to basically have this 3D system view of the HAT P7 system, showing that basically the closed-in hot Jupiter is in a high obliquity and likely retrograde orbit, but near polar orbit. And here, they show you the measurement of the obliquities that they have. In gray, here you have the dark gray would represent the 68% confidence levels. And it seems that basically it could be a retrograde orbit. This is important. Why? Because we can get a better understanding of the dynamical formation, history, and evolution of exoplanetary systems. So this is this would be a very costly thing. So you need the star to basically be a star that you can use asteroseismology to get their properties. It has to be a transiting planet, and it has to be bright enough, the star, to get radial velocities in order to measure these other things. And you can get a 3D view of the star planet system. I think it's pretty cool, but it's very costly. Um, and another thing, there are results from high resolution, high signal to noise spectra. It's try to find a chemical signature of planet formation. This is something that has been trying to be done. And I separate, I put it separately from the metallicity, because here we're talking about abundances of different elements with respect to iron in this case. Um, why we want to know that? Because with this is very tricky. You need a really high signal to noise spectra of the subjects, high resolution in order to calculate the abundances of each of these elements. For 16, for example, you et al. Did this for 16 planet hosts with and 68 comparison objects. Okay, so these ones are planet hosts, probably their rate of velocity, and the comparison objects are probably stars that were searched for planets, maybe by transits or by rate of velocity, and they couldn't find them up to a certain um, um, period, but that they have masses that are less than 10% of the Jupiter mass. Um, and they were trying to compare some result that was previously found by Melendez et al. I think it's 2009, that analyzed that the sun had this anti-correlation between the abundance of the elements and the condensation temperature. And he claimed that maybe all the stars, that have rocky planets, probably will have this negative slope in this plot, like the one, it's been shown here for Kepler 100, because of the formation of rocky planets. However, when they did this for the 16 planet host, this is a very recent paper, they realized that actually some of the hosts show positive trends with respect to the condensed temperature of these elements. Other ones have zero, basically, trend, and some of them show what was with the sun. This maybe is telling us these are very precise measurements. So trying to figure out if the measurements are wrong, I wouldn't compare that. Something that it can influence the results that you're seeing here. It's basically the comparison objects. Maybe these comparison objects do have planets and they just haven't been found. So you're trying to estimate things using a sample that is not the correct one. Um, but also all of these slopes related to the condensation temperature um, may represent different ways that are happening, or things that are happening when planets are forming around these stars. And they give examples like sequestration of rocky material, and that will make that the stars will be refractory poor, or possible ingestion of planets, and they should have then refractory rich. um, Difference in the time scale, efficiency, and degree of planet formation, or in homogeneous chemical evolution. So this paper basically did not find an ambiguous chemical signature of planet formation, in opposition with this Melendez et al. 29 paper. What is interesting is that Melendez is also part of this paper. And I think this shows how, the knowledge of the stars and their systems is changing through time. And something that we thought it was, rock solid, it may not be in a couple of years. And this is something that we have seen everywhere in exoplanets, especially for the stars. So the take home messages, it's already more than 1 hour, so I'm going to try to be very fast. um I think that the take home message that I want you to have from this talk, related to host stars, is that know the star, know the planet. Okay, if you don't know the star, um, your characterization of the planetary systems and the planets is not going to be reliable. The discovered techniques and methods prove different areas, populations, and types of stars, okay, because of their characteristics and how, where they can find planets and how did they do it, etc. Um, this is also true because for most of the planetary systems known until date, all what we can see is the star. This is not true for microlensing, but all what we can see is the star, and it's not also true for direct imaging where when you really look at the planet. But for the most successful ones, all you can see is the star, and therefore we need to know the star to get the bulk properties of exoplanets, right? And also because we need to characterize better the host stars in order to do these occurrence rates. um, we need to get to know the star also because we want to get really reliable orbital parameters for these systems, right? We want to measure if there's any eccentricity. We want to see the full configuration of the star so there is no ambiguity about how the system is. Also, because they can provide clues on planet formation or evolution of the system, right? What happens when planets are being created? It's material falling into the star. It's not. There are several results. For example, lithium. They're very controversial. That some groups find something and the other ones don't. So you can go and check those ones too. Um, Here I show you an image that comes from Mulder's 2018 from the Handbook of Exoplanets, one book that I really recommend you to look at, where basically tries to attempt to see where the planets are according to stellar metallicity and stellar mass, right? So what we have here is that giant planets occur more frequently around more metal-rich stars and more massive stars, and this supports the core accretion theory. The smaller planets are found around stars with a wide range of metallicities and occur more frequently around lower mass stars, around the M dwarfs. But they are, corrections, right? Some of this works up to 2 solar masses, and some of this actually works up to 5 Jupiter masses, right? As we saw before. So, for example, here, if we talk about the currents rates, things that I want you to remember is that The occurrence rate of giants increases as a stellar mass increases. However, the occurrence rate of subneptunes increases as stellar mass decreases. Okay. And for example, the occurrence of rate of giants decreases as a stellar mass increases from two solar masses. So these are, for example, things that we saw in the previous slides. And another thing that you can look here, it's the occurrence rates. For example, sorry, um, I put here the planets, but for example, hosts have higher average metallicity when compared with field stars when they host giant planets. And this is what it's known as the planet metallicity correlation. When we're talking about planets that have sub-Neptunes, super-Earths, etc., the hosts exhibit a large range of metallicities. They do not prefer metal-rich stars. However, the occurrence rates for Neptunes and super-Earths with periods less than 10 days are 3 times larger for metal-rich hosts. So here there is a little dependence on metallicity if we consider also distance, okay, not just type of planet. For example, for the Neptunes and Jupiters, if they have longer periods, they show longer periods around metal poor stars, right? And here it's the masses of these objects. If, for example, a super Jupiter is larger than, I think it's five masses of Jupiter, the average metallicity of the host stars show a declining trend. So basically, these are some of the things that we cover here. This can change. In 5 years, maybe we will figure it out that all of these results were not as we thought, or we can find another way to interpret them. So it's good to be curious and read a lot of papers and check these things often, because, for example, I was on a maternity leave and I realized that in all these 6 months, a lot of things has happened related to this. And I'm not even sure that I covered the most recent results. So I invite you to go and check the literature, check these things. For sure, the planet metallicity correlation for giants will hold. However, there are some specific things that are specific to samples of the stars that are related to the surveys, etc., that can change depending on how the data is analyzed, or if you get better data, for example, better parameters from high resolution spectra, or if you get those parameters from asteroseismology. So I hope you like the talk, and if you have any questions, we have, I think, 1 hour for that. I'm going to try to answer all your questions if you have some. So I see you then. Bye.